Hi, my name is Lisa, and today I will be talking about elastic hyperparameter tuning on the cloud. At the core of all machine learning is this curve of model accuracy over training time. Read through any machine learning paper today, and you will probably see a curve like this or an accuracy number, which is simply the accuracy attained by the time the authors needed to publish their results. This is a very limited view of the model training process, however. So let's zoom out and see what this process looks like over the weeks before this conference or production deadline. Each of the lines on this graph represent a model with different hyperparameters, where a hyperparameter is any parameter that can affect the model's training time. You can see here that there's a huge surge of possible hyperparameters that people try very close to the deadline in order to obtain a model with the highest possible accuracy. This process of hyperparameter tuning is the most compute-intensive part of the model development process. And since the space of hyperparameters is incredibly large and it takes a lot of compute to train even one model or trial to convergence, developers will launch a subset of possible configurations, stopping some of these trials early if they do not look promising in order to reallocate their available resources. The choice of hyperparameter has such a drastic effect on the final accuracy of the model that it's incredibly important to find and train an optimal or close to optimal trial, depicted here in red. It is this deadline-focused hyperparameter tuning that we're interested in for this talk. More specifically, how can we sufficiently explore the space of possible hyperparameter configurations in order to find a good trial and train it so that we can return a highly accurate model given a fixed deadline and resource constraints? Such an algorithm must balance the exploration of finding the best trial amongst the possible hyperparameter configurations with the exploitation of training that best trial to convergence to ensure the highest possible accuracy. If one wanted to explore possible trials, the intuitive thing to do would be to run each trial on a different machine in parallel. And if one wanted to exploit trials, they would want to give multiple machines to individual trials. This would allow these trials to train faster, and thus you would get a model which is trained for longer by your given deadline, which, as we've shown, is better for accuracy. One important thing to note about this exploitation, however, is that models scale sublinearly with the number of machines, meaning that after a point, giving more machines to a trial does not significantly increase throughput and in fact can decrease throughput due to communication overheads. It is this fact of sublinear scaling that makes current work in hyperparameter tuning inefficient for the cloud environment. Up until this point, hyperparameter tuning algorithms assume a fixed cluster where the user has a deadline and a fixed number of resources. On the cloud, however, the user's resources are not a fixed number of machines, but rather the dollar budget that the user is willing to spend on the experiment. Now, these two settings can both be translated to solving the same problem of how can we allocate machine time, or GPU minutes in our case, to trials throughout our experiment in order to get a well-trained model by our deadline. But the key difference here is that in the fixed cluster setting, one must allocate their GPU minutes uniformly across their experiment, while in the cloud environment, no such restriction exists. These elastic resources allow us to come up with an allocation that does not suffer from wasted GPU minutes due to sublinear scaling, and thus can lead to a model with a higher accuracy than fixed cluster methods by the deadline. In order to better understand why this is the case, we're going to go through an example of a current state-of-the-art hyperparameter tuning method on a deadline, Hypersked, to show how it can be better adapted to the elastic cloud environment. So here we've depicted the resource time allocation of Hypersked, which at a very high level performs sequential elimination, which means that trials are trained for a short amount of time and then evaluated. The trials which have good accuracy will be further trained, and the others will be killed in order for a new trial to be placed on that machine to be tested. This sequential elimination continues asynchronously up until soon before the deadline, at which point all machines are allocated to the best performing trial. If we were to move this to the elastic environment, we could do two things. First, we would no longer need to run things asynchronously, as we can spin up as many machines as we need at the beginning of the experiment. Second, suppose our model only scales to 3 GPUs, meaning that GPU minutes are wasted by using all 4. On the cloud, wasted GPU minutes means wasted money. So what if instead we had the foresight to move those GPU minutes to the beginning of the experiment to be used to test out a new trial? If this were the case, then there is a chance that this new trial would end up having the highest accuracy, and thus we would get a better model at the end. This idea that in the cloud environment, one should explore many trials on many machines in the beginning and deprovision machines as trials are eliminated, only keeping ones which would sufficiently increase remaining trials' throughput, is the core of our method and should be the focus of future work in hyperparameter tuning on the cloud. In other words, when it comes to machine time allocation of trials on the cloud, triangles are always better than rectangles. We used this idea, along with intuition from a previous work, Hyperband, to develop our method, SEER, sequential elimination with elastic resources. Hyperband's intuition is based off of the convergence rates of different models. If a model converges quickly, meaning that we're going to know its final accuracy relatively soon into training, it makes much more sense to employ a much more explorative strategy, where you're running many more trials, training them for far less, and not really assigning more than one machine per trial. But if a model converges slowly, meaning that we're not really going to know what the final accuracy is going to look like unless it is trained for a long time, we're going to want a much more exploitative strategy, since we aren't going to be able to know which model is better unless we train them all for a very long amount of time. The problem is that we don't know which models converge quickly and which models converge slowly, and there's no way of figuring that out during the experiment. So what Hyperband does, and also what SEER does, is employ this bracket strategy, where each bracket represents a different level of exploration and exploitation. In the case of SEER, an exploration bracket is a bracket which runs a lot of trials with very few machines per trial, doing sequential elimination, and an exploitation bracket also does sequential elimination, but with far fewer trials and with more machines per trial. This is beneficial in two ways. First is that you can account for cases in which your model converges quickly or your model converges slowly. Second, this helps when it comes to moving trials between brackets. To better understand that, we can look at this example on the screen. As we see, the yellow trial ends up having a better accuracy than the green trial early in the experiment. So what we're going to want to do is to switch them, so the yellow trial gets more resources and the green trial gets less resources. This is useful because the more that we train our yellow trial, the better we're going to know whether or not it's going to outperform the blue trial, and in the off case that the yellow trial is the best configuration, we're training it for longer, meaning that we're going to have a trial which is trained for longer and thus has a higher accuracy by our deadline. It's these facts that make SEER so successful in the setting of a fixed time deadline and a fixed cost budget. Lastly, SEER is able to deal with the sublinear scaling of models by ensuring that no bracket exists such that the number of machines per trial for that bracket is larger than is efficient for the scaling of that model. This is a parameter that the user sets at the beginning of the experiment and is a parameter that's pretty easy to figure out if you're familiar with training these sort of models. So we see that our method actually does quite well on various different benchmarks in image classification, semantic segmentation, and text classification. Given a deadline and a cost budget, SEER is able to get higher performance than all of these other methods. It's important to note that even though these gains may seem to be small, when it comes to something like getting a paper into a conference, these small gains are incredibly important. To see some more results about what happens when one varies their deadline or their cost budget, as well as some theoretical analysis, please check out our paper. Thank you very much.